From Photonics Media, this is the podcast that takes listeners inside the physical science of light as we explore groundbreaking and industry-shaping progress in lasers, optics, imaging, metrology, and sensing. Each episode, our hosts welcome optics and photonics luminaries, rising stars, and market leaders for robust discussion about the trends shaping the field of photonics. From research and development to commercial innovation, we're on the air for unparalleled insight, offered on All Things Photonics. All Things Photonics is brought to you by PolyScience and Lumencor.
Today's episode is brought to you by PolyScience. For over 60 years, the PolyScience line of award-winning temperature control equipment has been helping the photonics industry reach its goals safely and efficiently. Our products are made in America and delivered globally. Please visit polyscience.com to learn how we can help you. Changing the world of chillers is more than a tagline. It's part of our history. Today's episode is also brought to you by Lumencor. Lumencor excels in the manufacture of technical lighting, scanners and imagers, and metrology. Visit us at lumencor.com to see how we can best support your new products and OEM production.
In the words of Mark Twain, find a job you enjoy doing, and you'll never have to work a day in your life. A lot of people roll their eyes at this over-applied quote, and to be sure, its source managed to live an existence that avoided the spreadsheet. For our featured guest today, however, Twain's sentiments could not be more true. In fact, even in retirement, he hasn't stopped working. Paul McManamon is continuing his work solving problems in emerging technologies. Currently, McManamon is president and CTO of Exciting Technologies LLC and works part-time with the University of Dayton as technical director of the LiDAR and Optical Communications Institute in the Electro-Optics Department. Perhaps best known as the father of the optical phased array, his work has been foundational to numerous technologies and will be to many that have yet to be developed. His work at the Air Force Research Lab yielded advances in LiDAR, directed energy, and other sensing and laser technologies. Today's conversation touches on some of those topics, the optical phased array, directed energy, and LiDAR, as well as quasi-retirement. Up next, news editor Joel Williams speaks with Paul McManamon, president and CTO of Exciting Technologies, and after a short break, senior editor Jake Saltzman speaks with the brain trust of TeraView Technologies. Episode 7 of Season 9 of the All Things Photonics podcast starts now.
So I'd like to start by talking about some of your work in your early career, particularly with the development of the optical phased array, which is one of the things that you're known for. Tell us a little bit about what led to the development of that technology and where it's going now.
Okay. I first started getting interested in optical phased arrays about 1985. And I looked at what radar people did, and the beam was in one spot, it disappeared there and showed up in another spot. And I was thinking, man, I'd really like to be able to do that with the electro-optical systems. Unfortunately, we have very expensive, very complex, mechanically complex systems like gimbals, and I didn't figure they'd ever really be cheap or simple. And so, wow, it sure would be nice if we could begin to do some work where we just changed phase and the beam moved. And so I was in the government at the time. I ended up having 3 contracts in 1987, then 2 years later. One with Hughes, one with Raytheon, and one with Westinghouse, looking at how to steer with no moving parts. 2 of those were liquid crystal oriented, one was acousto-optical oriented. And in any event, that's sort of the start of my interest. I ended up staying very involved with liquid crystals for a while. In the 90s, had a lot of work with Raytheon. DARPA then in the 2000s had something called steered agile beams with 15 different contracts, all looking at different optical phased arrays type approaches. More recently, we've made a lot of progress. If you look at space-fed optical phased arrays, which is what I'm interested in mostly, you steer one dimension and then you steer the other dimension. The nice thing about that is you have a lot fewer electrodes than if you have individual transmit-receive modules like you do with a radar. If you look at a radar like the F-35 radar, it has a little under 1,700 individual elements. They do 2 dimensions at a time, but it's around X-band, which is around 3 centimeters wavelength. When you change that by a factor of 20,000 in wavelength, getting up to 1.5 micron, you then end up having 20,000 times squared, 20,000 squared times more electrodes. So you end up with hundreds of billions of electrodes. And so I'm a big advocate of what's called space-fed optical phased arrays. So I can steer in one dimension, then steer in the other dimension, and that can limit the addressing to something's reasonable. The biggest problem that we had with optical phased arrays was something called fringing fields. And I could explain a little bit more about what that is. But that basically says that if I have an active medium this big, then I can't address it. I can't change faster than about that distance in the cross range. And so in any event, we've solved that problem so you can reset quickly. So I'm expecting optical phased arrays to begin to be available fairly soon. That's one of the things that I'm emphasizing with my company. I worked on this a lot in the government, and I'm still working on it with my company, and ended up having 20, 30 patents or something like that in the region.
Right. Now, what are some of the applications for the technology?
Oh, the application space is huge. It's actually bigger than microwave phased arrays. You can start with the idea that you can use it in manufacturing. If you're doing additive manufacturing, you want to use a laser beam and you want to write and whatever else. Well, if you can move it faster, that's good. We can do more than one beam at a time so that we could spread out and heat an area and then have another write beam that is inside that. Then you move on. That's in the factory. That's simpler because it's inside. Then you move on and you could, for example, revolutionize LiDAR because you can steer very quickly. You can have random access. You could acquire with a passive sensor that's fairly big and then look anywhere in there. You could use it for directed energy weapons, which it's very good for that because you can steer very, very precisely. With an optical phased array, you should be able to steer to 1/100th of a diffraction limited spot size. Because you can steer to such a fine angle, it's really good if you want to go for long distances. And if you went to strategic directed energy, you'd be in long distances. You could also use it for free space optical comm, which I think is going to be the future, certainly in space. And I think it's the future in battlefield, a combination of low data rate, height in the noise, height in the clutter, microwave comm, plus free space optical comm. Optical comm has a problem with clouds or fog, but RF comm has a problem with dying, with the fact that when you're on your radio, there's incoming, they direction find, they're sending ordnance to kill the spot where you're at, plus jamming. And there's infrared countermeasures that these could be applied to. So I think that the application space for optical phased arrays is huge, starting in the factory and moving out to revolutionize the battlefield.
Excellent. Now you mentioned directed energy, and that's something I'd like to get into a little bit more. That's an area that definitely seems to be gaining a lot of steam these days. I see a lot of news about different companies working on directed energy projects. And I was wondering if you could kind of give us an idea of where things are currently. What kind of threats are we currently able to address? And what are some of the problems that we're seeing, in building these systems? What are some challenges that we're having to overcome there?
Directed energy is coming along. Directed energy is becoming mature. Lockheed Martin made a 300 kilowatt electric laser not too long ago. If you look back 10, 15 years ago, we had the large airborne ballistic laser, I forget the ABL, but in any event, it was megawatts and it could do strategic kill, but it was a chemical laser. People don't like dragging chemicals into the field. So the idea at the time, I think Bill Gates was our Secretary of Defense, he said, gee, we don't want to deploy that. We want something that's electric. And it's taking a while, but we now have 300 kilowatt. I assume will be a megawatt in a not too distant future. Plus, for tactical applications, you can do things at shorter range, shorter distance, shorter range. I think the biggest challenge, in my opinion, for directed energy, the U.S. is going to something called mosaic warfare, where you'd like to disaggregate. You'd like to have a lot of inexpensive platforms and you'd like to have inexpensive kills. Directed energy is wonderful in some ways, in the sense that you can do a kill for 49 cents or 13 cents or whatever. A little bit of light and you get a kill. And it's got a completely unlimited magazine. So long as you got electricity, you've got bullets. So that's really, really neat. The problem is these are big, inexpensive systems. So how many big, inexpensive systems can you build? So what you'd really like to do is you'd like to have those 49-cent kills, but with smaller systems where you can disaggregate and you can get more of them. The bigger systems might be fine if you're defending Guam or something like that to incoming missiles, because you can put them on the ground, and or people in Israel defending against the Katyusha rocket or something like that. But I think one of the real challenges for directed energy is how do you build smaller systems? It's not just going to higher power. It's trying to make systems that are affordable enough that you can buy a lot of them. The inexpensive price per kill is wonderful, but the cost, the big heavy cost, the big size, the mass, whatever, of the systems that do that are not so wonderful. So I think the thing that needs to be addressed is a question of how in the world can we make these systems so that you can afford a lot of them and you can dispose them everywhere.
Right. Now, you mentioned that the optical phased array kind of factors into directed energy. Could you kind of expand on that?
Well, sure, because an optical phased array is going to give you random access and very, very, very precise pointing. If you want to go long range, you need precise pointing. If you'd like to look at an area and you see an anomaly here, 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 and you want to randomly hit that one, hit that one, hit that one, hit that one, or you've got a number of missiles coming at you and you'd like to, to stop all of them, you're going to have to go from one spot to another to another. I think optical phased arrays will contribute to making directed energy weapons smaller, lighter, cheaper, because they are electronic. You get rid of some of the mechanical complexity. And once you build circuit, we all know once you build integrated circuits and stuff, things get cheap. They get smaller, lighter, cheaper. And so initially optical phased arrays will probably be expensive, but over time, as we learn to use them, as they get deployed more, they're going to become a lot cheaper and a lot more reliable than mechanical systems. So I think they should enable making directed energy weapon systems cheaper, as well as being able to point more accurately and random access and faster.
Excellent. Now, sort of doing the background research, it's very clear that there's, just so much technology, that's incredibly important, both in the defense world as well as the consumer world, that, kind of stems from the work that you've done or, has benefited from it. In one of the many areas that you've touched and, one that you're, quite active in is LiDAR. Could you tell us a little bit about your work with 2D LiDAR? And then, maybe kind of a stupid question, but, what's the distinction between LiDAR and LiDAR?
Okay, let's do LiDAR versus LiDAR.
Sure.
Back a while ago, I would usually call it laser radar. Then it got to be that if you said LiDAR, people were talking about a hard target device that used a laser to make a 3D image that bounced off something and came back. And if you said LiDAR, it would be soft target, things like chemicals or the atmosphere or ballistic winds, things like that. Then it sort of blurred, where if you are a automaker, you use the term LiDAR, you don't use the term LiDAR. And you use it for everything. So LiDAR and LiDAR have pretty much mean the same thing nowadays. Most people use the term LiDAR, and the most popular spelling, if you will, is capital L, small I, then capital DAR. And when I was expert witness for Uber against Waymo/Google, no matter whether I'd write LiDAR or LiDAR, the lawyers always made it LiDAR with the small I capital and the other small I and the capital for the rest of them. So the reality is LiDAR and LiDAR nowadays mean pretty much the same thing, but LiDAR is more prevalent, it's more common. And I forgot what the other part of the question was.
Yeah. Could you just tell us about your work with 2D LiDAR?
Now, 2D LiDAR, that started in the early 90s. And the idea was we used to fly, the Air Force, I was with the Air Force, we used to fly low, 300 feet or 200 feet. You'd pop up to 1,000 feet and drop your missiles, or put out your munitions. Then when we hit the first Gulf War, we started flying at 20,000 feet and dropping bombs from there, because the reason we flew low before is if you were in Vietnam or whatever, they had the SA-2, the SA-3 surface-to-air missiles that would shoot at you. So you'd fly low in order to be safe, to not have somebody shoot at you. You'd pop up for a short time and you'd shoot. So we had something called the Lantern Pod, before that the PAVE TAC. They used thermal imagers that were long wave. They could identify something in the 3 to 5 kilometer range, which is fine when you're at low altitude. But when you go to 20,000 foot altitude, they couldn't hardly identify anything looking straight down to the ground. So I wanted to be able to identify something 20 kilometers out. We already had a laser designator on board. So then the question is, why don't you use that laser designator? It's already there, and make an image with it. You're much shorter wavelength. You're going to have longer range. And so we started just using the designator and making a two-dimensional LiDAR. You don't need high bandwidth detectors. We used an intervac, electron bombardment type of camera, and we came up with a two-dimensional LiDAR. Later on, people did 3D, and those are still out in the field today. Those, like you're using something like that with the Northrop Grumman Lightning Pod. That type of technology has been incorporated in there, and it gives you a much longer recognition range than we had before. It's a recognition range where you can fly at 20,000 feet and see things out far enough that you could drop a bomb in time. Whereas otherwise, with the short range we had just using the thermal imagers, then you just wouldn't see far enough.
Right. Now, you led a discussion recently at the Defense and Commercial Sensing Conference, noting the lack of vendor-independent standards for LiDAR performance markers like range, resolution, accuracy, field of view, and so on. Could you tell us a little bit about what led to that discussion and what might come in the future in terms of testing and benchmarking?
Sure. I chaired a National Academy of Sciences study on laser radar /LiDAR/LiDAR, which was like 2015 or something like that. After that, I was talking to people in the community, and I became aware of the fact that there were no standards for how you test a LiDAR for cars. So if General Motors, if Mercedes-Benz, if Toyota wants to compare LiDAR 1, 2, 3, they all did it different, and there was no standard procedure. So I thought, gee, it'd be nice to do something like this. I started talking to my friends at SPIE, where I used to be president before. It's an optical society. I said, gee, it sure would be nice to do some measurements to help create standards. We would have started doing these measurements earlier, but then COVID occurred. So the first one would have been 2020. As it turns out, it got delayed. The first one was 2022. And we've done a third data collection where we get a group of 9 or 10 auto LiDARs and we measure their performance. And we're trying to develop a standard method of measurement. Then the other thing, that it was great having SPIE do these, but SPIE does not do standards. So then I talked to SAE, the Society of Automotive Engineers, and I ended up becoming chairman for a LiDAR task force under the Active Safety Committee of SAE. And the idea there is to write a report first, and then eventually we would like to have standards. And as a goal, I'd like to have those standards not just be in the United States, but be in the United States, Europe, China. I'd like to work with our friends all over the world so that when an auto LiDAR or when auto company or a tier one provider wants to compare this LiDAR against that one, they've got a methodology for how to do that. One of the problems associated with that is if you talk about just an auto LiDAR, some of them might be 30 to 50 meter range. Therefore, a car that's going, therefore, say a car driving in the city that's at 30 miles an hour. But if you're going to drive on the Autobahn, 30 to 50 meters doesn't cut it. You're going to have to see a couple hundred meters or farther because you're going fast. You want to be able to see far enough that you can stop when you see it. And so all the auto LiDARs are different. You're not, you can say this one's better than that one, but the reality is they may be in completely different categories. If it's a long-range LiDAR for the Autobahn, that's completely different than a short-range LiDAR. And I'd really like to include even things like, if you've got a LiDAR for Amazon trying to deliver, goods with their quadcopters, or if you want to go in and out of a store, and they want a 3D image of it, those are very short range. So I'd like to incorporate those as well. And part of the problem is trying to come up with standards that have standard test approaches that might apply to a significant variety of LiDAR types.
Right. Now, what would that entail exactly? How would what would be the next steps for that?
So we are doing measurements. What we're trying to do is to measure how many points in a point cloud you might have at a certain distance with a certain reflectivity. And you should be able to develop reasonable standards as to how to measure things. But then, in addition, there's issues like, what happens if there's a stop sign right next to it? Let me give you a scenario. One of the more interesting cases for the city is you've got a little kid who can just barely walk. So they're fairly small. I estimated 80 centimeters high and 15 centimeters wide. They step out from between parked cars. You want to see that kid. You want to be able to stop. You want to avoid hitting the kid. But now what happens if there's a stop sign there? A stop sign has embedded corner cubes. We found in our first year of data collection, there were LiDARs that worked very well seeing this canonical little child. But then when you put a stop sign next to it at the same range, they didn't see it. So you need to come up with the basic standards, here's what to measure, but then you also need to see confusers. What happens if there's corner cubes next to it? What happens if there's stop signs with embedded corner cubes? What happens when there's rain or fog? When the weather gets really bad, everybody ends up eventually slowing down or stopping. The question is, how does an autonomous vehicle using a LiDAR do as compared to a person who's just working with his eyes? And so we need to begin to understand a basic set of measurements, and then a set of measurements with confusers, then a set of measurements with confusers and weather issues.
Right. Now, pardon my ignorance, but what's an embedded corner cube?
An embedded corner cube might be, well, what I'm saying there is they mix these little corner cubes inside the paint. And so when you paint them, instead of having a 2 pi steradian radiance angle coming back, it's going to have 10 degrees or something like that. Almost all the light is going to come back in a smaller cone of where the light is. And because of that, it's going to get a much higher reflectivity than if the light was scattered as a Lambertian scatter. If you just have normal white paint, you get a Lambertian scattering over a wide angle 2 pi with a cosine distribution. With a corner cube, it gets much smaller. Now, you could have corner cubes that are embedded in the paint, but there's also, if you've been driving on a rainy night, you'll sometimes look down and you can see where the lane is because they'll have corner cubes embedded in the asphalt as lane markers. And it's much, much easier to see in a dark, rainy night when you have got those corner cubes embedded in the, in the lane markers.
Right. Okay, great. Now, the next question. Elon Musk, who's certainly not necessarily a reliable or maybe qualified source, rather infamously called LiDAR a crutch. Ironically, Luminar just noted Tesla as one of their biggest customers. And people who are actually working in this technology, have fired back and said, LiDAR is essential. And from what I understand, when you're building a vehicle with any degree of autonomy, you want to put in like a lot of fail-safes and redundancies in order to kind of build something as safe as possible. And so from my perspective, LiDAR seems, pretty important because, just because it's another source that you're getting information from. I was wondering if you could kind of give your perspective on the importance of LiDAR when it comes to, these advanced driver assistance systems and full autonomy.
I think it's extremely important. One of Elon Musk's arguments, I think, initially was, gee, people drive all the time and people do pretty well. And they do if you don't mind having 35 or 40,000 deaths every year in the United States from the road. I prefer having 3 or 4,000 instead of 30 or 40,000. Or I'd prefer having 300 or 400 instead of 35 or 40,000. I'm a big advocate of all of the above. So if you can make the sensors cheaper, then I think, we can begin to use all of them. And LiDAR gives you not just a two-dimensional perspective, but a three-dimensional perspective with good resolution. Radar is good, but radar doesn't give you the resolution. It will see through weather. Now, the other thing you should be aware of, though, most of the radars for cars are millimeter wave radars. If you're in heavy rain, the LiDAR will actually see through that better than the millimeter wave radar. The millimeter wave radar does better in fog because of the particle size, but in heavy rain, LiDAR actually does somewhat better than the millimeter wave. So, as I said, I'm a big advocate of all of the above. The other comment I would say is I think sensor fusion is very important. I remember hearing the first time someone died in a Tesla. I was watching Harry Potter, apparently, so he shouldn't have been doing that. But there was a radar. My understanding is there was a radar on that particular Tesla. The problem was it confused the side of a truck, which was white, with the horizon. The radar didn't confuse that, but they must have used the passive sensor as the preferred sensor that decided the range. And with a white screen, it couldn't tell what the range was, so it got confused. So one of the other challenges for autonomous vehicles, I think, people do a really good job of fusing the data. But if you've got a radar, if you've got a LiDAR, if you've got a passive sensor or two, then you've got to somehow figure which sensor to use when in an optimum way in order to do the best job. But LiDAR, I think, is an absolutely critical sensor. It gives you good resolution in angle-angle space, good resolution in range, and it gives you a 3D image. And so I think that's going to be a very, you could call it a crutch. You could use your eyes call your eyes a crutch too. More information is good. And so I'm very much of an advocate of 3D LiDAR information and maybe even velocity in some cases, a coherent LiDAR. I think it's very useful, and I think fewer people will die on the road when we can have them.
I think I would co-sign that. Now, when we met at the Defense and Commercial Sensing conference last month, one of the things that kind of struck me was, you're retired. Normally, in retirement, people take up, woodworking or bird watching, or that kind of thing. But your retirement looks a little bit different. Could you tell us a little bit about what you're up to these days?
Okay, yeah, my wife says I flunked retirement. Retired from Air Force Research Lab. I was chief scientist of the Sensors Director at Air Force Research Lab in 2008. I now have grad students. I did have 5 till not too long ago. 3 of them graduated. I'm down to 2 now. I have a small company with 9 employees. I'm also chief science officer for another small company called TeraView that will 3D map the world from low Earth orbit. And basically, I'm having fun. And sometimes people pay me. People ask, when will I really retire? And the answer, well, why would I? I'm having fun. I want to do this regardless. Some people have fun one way, some people have fun another. I enjoy science, I enjoy technology. This is what I do for fun, and sometimes people pay me. And so, that to me, that's a great retirement.
Awesome. Sounds great to me. Now you mentioned Exciting Technology, your company. I was wondering if you could tell us about, some of the projects that you're working on there that you're particularly interested in or excited about.
Well, we are very interested in non-mechanical beam steering and mechanical beam steering. We've got, probably close to 30 patents or something like that, either in process or already granted, for steering laser beams, primarily laser beams that are narrowband. I mean, that's something I've been interested in for a long time. I discovered that there's a number of mechanical approaches we can do now, and that's neat too. And eventually then, and it isn't that far out in the future, I think within a few years, we'll begin to have optical phased arrays that we can deliver to a number of people. We also are doing a lot with free space optical comm. We've got a standing experiment here over 400 meters. We're embedded with the University of Dayton Electro-Optics and Photonics Department. I wear a hat there with graduate students, and I've got then people who work for me with both roles. They can work on one bench as Exciting Technology, turn around and work on another bench with the University of Dayton, and both work for me. And so there's a huge synergy between the two, I think. But we're doing 11 gigabits per second continuously over a significant region, over 400 meters, and watching how it does as a function of weather. We're just getting a new contract on laser vibrometry. You can use laser vibrometry to see what's going on. Like a graduate student 20 years ago that I saw his PhD dissertation talked about how you can tell whether a bridge is wearing out by looking at the vibrometry spectra when trucks go over it. Are there more cracks developing in the bridge? From 2002, the Air Force did a data collection from North Oscura Peak to Salinas Peak, 52 kilometers away, over 30 miles. You could look at an SUV and you could see whether it was running or not. You could see if you hit the horn. You could see if people were talking in it. We couldn't, aspirationally, you could see whether it needs a tune-up or not. We didn't actually do that sort of thing, but you should be able to see because every cylinder has a unique misfire characteristic. So we're doing a laser vibrometer. So I guess those, I think the steering is one of the big things, various LiDAR approaches, and then the free space optical comm. Yeah, eventually I'd like to do some more with directed energy as well.
Excellent. Thank you so much. This has been such a great conversation.
You're welcome. Enjoyed it.
Awesome.
For our listeners and readers over the last 18 months, the terahertz band has become a familiar subject. We've enjoyed conversations with leading R&D figures like the UCLA-based optoelectronics luminary Mona Jarahi, an exclusive interview with a leadership team of non-destructive testing and award-winning startup Track, and feature articles about topics ranging from art inspection to forgery detection to semiconductor manufacturing. Today, we continue the theme with guests Alasdair Pentland and Andy Bell of Cambridge-based terahertz solutions firm TeraView. With a focus on core inspection applications and thin films and batteries, as well as coatings thickness, it is as understandable as it is apparent that the terahertz band today is a vital resource for the aerospace and defense e-mobility sectors. While there are still other industries that rely on terahertz-based inspections and many more on the way, the wave of momentum driving the adoption of terahertz solutions has been nonlinear. And that reality alone influences the how and the why of our frequent content spotlighting these solutions. It does not, however, aim to diminish the importance that working within the bounds of the terahertz band has shown for industrial applications. Quite the opposite, in fact. In our interview today, we dive into the aforementioned core applications and discuss the range of imaging and sensing modalities that optimize terahertz sources for particular applications. Understanding the properties of terahertz light is vital to deploying it properly. Just as critical, knowing the nuances of a given application. Senior Editor Jake Saltzman, with TeraView Senior Engineer Alasdair Pentland, and VP of Business Development for Automotive and High Value Coatings Andy Bell follows.
I'd like to begin with you two deciphering for our guests what qualities of terahertz light make the terahertz band an optimal solution for certain industrial applications. Tell us about terahertz light.
Well, the advantages of terahertz light is, as an optical technique, it is non-contact and non-destructive. And the terahertz beam can be adapted for both reflection and transmission geometries. Simple optics also allow other measurement parameters such as spot size, depth of field, focal length to be selected to suit the particular application. Terahertz frequencies are also completely safe and non-ionizing, unlike some of the other measurements techniques with high penetration. Terahertz time domain spectroscopy is a pulse technique, giving both time of flight and spectral information. Coupling these two measurements together generates a powerful technique for understanding both the thickness and dielectric properties of the measured film. This allows us to isolate spectral information from specific reflections in a complex layered sample, increasing both the accuracy and precision of the measurement. The long wavelength and large wavelength range of the terahertz light is also an advantage for these for two reasons. Firstly, it has a large penetration depth, allowing measurement of a large range of samples. Secondly, it reduces the effects of scattering from particles and surface roughness, which is very important for materials made of composite particles like ceramics and battery electrodes.
The applications that I think we're going to aim to discuss today are battery and industrial film applications, and then also paint coatings. And with paint coatings, we're talking about cars, but also craft, right? Aircraft, which veers very clearly into what we might consider aerospace and defense. I want to ask a sort of a timeline question. Obviously, the terahertz band supports these applications very nicely, but the recognition and the acceptance maybe of terahertz has been a slow adoption. Is there a reason behind that, an impetus for why it's taken a bit of time for, I'll even say for us, to have these conversations about terahertz light?
Yeah, I mean, terahertz has taken some while to mature. Initially it was a laboratory experiment. And it took some time for engineers and scientists to develop that from a laboratory application. And now they are production ready. They're suitable, they're ruggedized, the algorithms are optimized. So it means that we don't have to have specialists operating this or scientists. We can make it available to the general plant production people to operate that, which has allowed people to be more willing to put it into plants. And as you say, that's allowed us to address far more applications. So you're quite right. We talked about automotive body measurements and aerospace body measurements, but we also look at things like turbine blades in aircraft or semiconductor manufacturing, battery production, or thin film polymers, thin film plastics, and coated pipelines. The number of applications is just increasing. Almost weekly or daily, we'll get an inquiry from a customer saying, "Can terahertz do this? Can terahertz do that?" It's matured to a level where we're constantly pushing the envelope for these applications. And in terms of why this has happened, another of the drivers has been increased computing power, together with advanced algorithms. 15 years ago, the computing power we had in our desktops just wasn't able to handle the vast quantities of data or the throughput of the processing speeds to make it viable for a real-time production. So the technology behind it has increased, as well as the terahertz technology. And from our side, from TeraView, we've constantly been evolving the hardware. So we manufacture our own emitters and detectors, and we've been moving them forward as technology has allowed. So we're constantly pushing the threshold as to what you can get from the terahertz, which has allowed us to make more stable, reliable, and reproducibility of this equipment.
So you raise a very interesting point. Anytime you weave into a conversation the types of dialogue you're having with customers, that's always a fascinating dynamic to prod. And we will in a moment, but it occurs to me that we might want to, for our listeners, get a sense of what TeraView, excuse me, is doing. Tell us a little bit about the company.
So the company was formed about 30 years ago as a collaboration between Toshiba Corporation and Cambridge University. We were actually the first R&D center outside of Japan for Toshiba. As about 20 years ago, Toshiba had some financial constraints and they had to pull all of their R&D back to Japan. So TeraView became a private limited company 2001. And since then, we've focused initially on semiconductor because that was where we were working with Toshiba. But we've been developing terahertz solutions to solve industrial problems. And over the years, we've measured such things as the enamel on your teeth, cancers in the human body, explosives with the TSA, and then more mainstream industrial applications, the automotive body, the aircraft and plastic films and so on.
You've mentioned a number of application areas, I will say, and certainly things like semiconductor and work with the TSA to gauge explosives. In the last 25 years, those have evolved in quite distinct ways. But I want to get a sense from you where, in your mind, the progress has really been. Because with the terahertz band, you have very distinctive terahertz sources. There are laser optics considerations. And then, of course, there are the applications. Where has the progress been most prolific in your mind?
The advance in all the growth areas have been the automotive. Mm-hmm. So we are working with several large global automotive manufacturers. We're the preferred suppliers for several of these, and others are all adopting this now because it's overcome the limitations they had of their previous technologies. The battery industry in particular is going through a massive growth, and the number of gigafactories and the demand for the battery applications is driving a lot of that growth. So they're probably the two areas that are having the biggest growth areas at the moment.
We talk a lot about, for example, lasers for e-mobility, and that's a very photonics first angle into a broader subject. I want to ask you about EVs and e-mobility more broadly. Can you just put into context for our listeners the size or the weight of the impact that's poised to have on battery manufacturing, and then as a result on a company such as your own that plays in that space?
Yeah, I mean, at the risk of repeating all the cliches you'll see on social media, EVs are here to stay.
Yeah.
The bans coming in from the various governments on internal combustion engines, whether it's 2030, 2035, 2040, they're coming, and there's no two ways that's going to happen. But it's crazy. We're in this situation where we're moving to electric vehicles because we want to be greener, we want to cut waste and everything. Yet the battery manufacturing industry produces at the moment up to about 30% scrap waste on the battery electrode manufacturing or battery cell manufacturing. So we've got a greener technology we're adopting to get rid of waste, and we're creating waste. And there's about $170 billion going into that by the year 2035. So if we're going to scrap 30% of the cells, it's a huge amount of dollars being thrown away. Adopting terahertz as a measurement technique in that manufacturing process, the estimates are we can get that scrap down to about 5% or slightly under 5% because it's real-time measuring. So we're able to optimize the process during the manufacturing, so they're not getting these scrap electrodes going through the whole manufacturing and testing them at the end. We test them in real time, we reduce the scrap, so we're actually living and supporting this move to green technology.
Just in terms of methodologies, I know, Alasdair, you mentioned in the intro terahertz spectroscopy, but there are other modalities, right? And you have to select the optimal modality for the application. You know, we've come across terahertz radar, for example. That one is still probably a little more rooted in R&D than industry, but nonetheless, the point remains, right? You have to select the optimal mechanism, the optimal deployment for the technology. In terms of distinct measurement mechanisms that rely on terahertz light, and particularly for inspection, what are some of the characteristics that you seek from the instruments used in this application? Thin films.
So yeah, the measurement technique used is obviously optimized for the information that you want to get from the sample. So the simplest technique we use is for films where we just want to know the thickness. And to measure the film thickness, we use a very simple time of flight measurement. The time domain spectroscopy is a pulse technique. So we transmit a pulse, it's reflected from the interfaces within the sample, and we receive those pulses. And the time between those pulses is directly proportional to the thickness of the film once it's been corrected for the refractive index. And this simple technique is very precise and accurate, purely because of the simplicity of the measurement. The optical delay between the pulses is generated by a delay between two different laser beams, and a very small offset in those beams produces extremely fine resolution of the time of flight of the measurement. And I'd say the advantage of this technique is the fact that actually you do not need to know the precise amplitude of the signal or anything like this. All you're requiring is the time of flight, which produces extremely precise and accurate thickness measurements.
One of the things that has emerged in our conversations about non-destructive testing, be it terahertz, be it a photoacoustic method even, is that people often have, customers, end users often have some familiarity with something like industrial X-ray, right? They've heard the term X-ray, and therefore there's some comfort there, even though they don't really know how an industrial X-ray operates. Andy, you mentioned talking to customers and receiving the type of questions, can terahertz do this? Is there a sense from end users, from customers or prospective customers, that they understand ultimately how simplistic some of these measurements can be?
I think generally, no, they don't. And this is probably one of the things limiting some of the adoption, is having to educate the customers on this at this stage. Generally, once we get in there and talk to a customer, we can explain to him how powerful terahertz can be, accuracy and speed of measurements and reduced calibrations and so on, and coupled with the stuff that Alasdair mentioned earlier, the increased safety, it becomes a very simple message to articulate to the customers.
I think too, and this is your area of expertise, but I think it's clear to say that durability of the technique and of using the technique is a real advantage. Certainly measuring paint thickness, though, for example, versus a pharmaceutical, different requirements on the measurement mechanism there. Two very different measurements. In terms of optimizing the source for the application, what are the variables that systems designers need to consider?
So again, coming back to the complexity of the measurement, if you have a simple technique like the time of flight technique, as I say, other than the optical design of the head, so that the focal length, the depth of field, etc., is suitable for the measurement, the design of the system is relatively simple. The requirements and the complexity and the difficulty of the measurement as it increases comes in where you have multi-layer samples, thin samples, or samples where you require information about both the dielectric properties of the sample and the layer thickness. These measurements are more complex because not only do you then need to know the thickness of the sample and therefore the time of flight of the measurement, you also need photometric accuracy of the measured signal. And this is done typically with a reference system. And obviously your measurement is accurate as the stability of the system has been since you've taken that reference. So again, in the industrialization of these products, going from the lab-based systems where you took a reference and then you took a sample a short time later and the system had to be stable over that short period. For these industrial applications, we're now seeing that it's got to measure continually for long periods of time. There is no time to take additional references, which is why the development of the system has included things like self-referencing. The systems essentially internally monitor their own signal and allowing the system to correct and adjust for any variations in the system. So we can now see that the stability of the system over many, many hours, days, weeks, is of a similar level to we're getting within, a few minutes 20 years ago. So
Yep.
That's another reason why the systems have been, incorporated into the industrial processes.
Mm-hmm. I want to ask too, just continuing this conversation or this theme anyway. Another boon to the terahertz market has been this notion of handheld instrumentation, and that lends to durability and portability. And we're particularly talking about scanners, but handheld isn't always optimal, right? If you're measuring a large aircraft or potentially a spacecraft, right, it's hard to do a methodical, scan with your hand. What types of systems are being used in the aerospace and defense system, particularly for paint removal and for paint evaluation?
So typically we are not finding that the handheld systems are applicable to these kind of industries. It's very much a data-driven world whereby there's a requirement to measure the same location very precisely on every single system that you're producing so that you can monitor how your process is actually behaving at a very fine level. The amount of data that factory automation systems are handling is very large. So handheld systems are not capable of taking information at the same locations repeatably enough, and they're not capable of taking it fast enough for the requirements of these kind of production systems. So we're seeing that, the measurement systems that are being doing are mounted on robots for taking precise location measurements quickly, or they're mounted on gantry systems where you've got moving webs, where you've got a continuous measurement of a sheet. So these are much more popular than any handheld measurements that are being done.
Go ahead. Sorry.
So the other thing we're seeing is that there are advantages of the automated system. One of the key measurements we make in the one of the key measurements we make in the aviation industry is looking at turbine blades. And obviously these are quite small structures, or rather they've got complex surfaces, and the requirements of the film layers are very critical to the performance of the system. And therefore the measurement location positions and indeed the ability to measure the whole surface is vital to actually being able to say that piece is safe and worthy of going in an aeroplane. And again, this requires the design of a specialized head and the location of a robot in order to be able to do that measurement in the first place. It's just not something that a handheld system is going to be able to give any useful information at all, really.
That's right. And I appreciate that explanation. I think that's very helpful. For my next question, and this is as I suppose the more technical aspects of any solution grow, there are other challenges. And I think any spectroscopist, any photometrist, any scientist will tell you that the data you get out is only as good as the data you put in. And that creates another challenge when you're working with complex shapes, complex structures. Has that been a theme for TeraView or for terahertz technology just more broadly? Because as you mentioned, Alasdair, these are very difficult structures to mention. And yes, you can use a more automated solution, but progress there has to happen too, right?
Yes, that's true. And but you know, working with CAD models, etc. You know, the shape is very well known, even if it is complex. And using software evaluation and design, you can then model the way that the robot has to move to interact with that shape. And again, you can model the way the terahertz beam is located within the sensor head, and therefore doing it, if you like, an overlay, a mesh of those two systems, you can then generate a comprehensive review of which parts can be measured, which parts can't be measured, and the best way to do it.
We've talked about you know, the I don't know if roadblock, but the maybe hesitancy, the delay in widespread mainstream adoption of terahertz technologies. And certainly things like the terahertz gap have been spoken about for years, and I'm not sure that phrase really applies so much now as it did maybe 15 years ago, even then. Where are the obstacles, the bottlenecks now? What is this is another way of asking, what is TeraView working on? I mean, what must happen in order to continue this forward momentum that we've seen in the last 5-10 years?
I think that what we need to continue doing is pretty much like we're doing now is keep evangelizing this message, but it's also about proving to many of the customers that this is a viable technique. You know, it's you know, well-known saying, you know, it always works on PowerPoint. You know, we can go and talk to the customer, we can show him all the pictures and all the diagrams and all the nice words, but the proof is whether it actually works. What we're tending to do now is engaging with customers, and when they get very interested, we will take samples from them, and that's where Alasdair and his team will come in and do a proof of concept evaluation. Typically, when a customer sees that, they can see the quality of the measurements, the accuracy, and the reliability. And from then, it's a much easier discussion with the customer. So it's about getting that mindset of the customer to believe it, and it's a belief is probably the thing to get past the gap.
Yeah, very good. And I want to end with this, and this is sort of an off the path we've charted question, but you mentioned the origins of the company, and there was a heavy R&D focus, right? There was an R&D center aspect of all of this. And it wasn't long ago that we were affiliating and associating terahertz light with these very large sources, right? For electron lasers, synchrotrons even. Just on the R&D side, in terms of terahertz, you know, what is underway in the research sector now? Because it wasn't long ago that the entire terahertz sector was very tied to the R&D center.
So from at a high level, we're part of the R&D is we're looking at developing a high-speed measurement technique. So particularly in the web processes, in the batteries, customers are wanting to run their production lines faster and faster, obviously. So the higher speed we can take measurements enables them to speed up their production lines. So we are developing higher speed measurement systems. We're also, as we said earlier, terahertz enables you to do more than just the time domain measurements. We can also take measurements within the frequency spectrum, which means that we can do more than just a pure thickness measurement. You know, some of the other traditional techniques will only give you thickness. For example, in the battery industry, we're measuring density, loading, conductivity, and we're constantly challenging ourselves as to what is the next measurement or solution we can solve for industry. So these are the developments we're working on. I can't be too specific on some of these because they're still in the R&D and IP phase. But we do have a number of additional measurements coming from that initial measurement of the terahertz waveform.
Well, keep us posted. Alasdair, Pentland, and Andy Bell, I appreciate your time, the brain power of TeraView, kind enough to join us on All Things Photonics. Appreciate your time. Do keep us posted, and best of luck with everything moving forward.
Thank you very much.
Thank you.
With that, we conclude another episode of All Things Photonics. Thank you to our sponsors, to the technical staff behind the scenes, and to continued support from the Photonics Media editorial team. As always, questions, comments, thoughts, and ideas are welcome. Let us know how we're doing via email at allthings@photonics.com. All Things Photonics is available on all major platforms and on our website, photonics.com.